And the guy who came along and started figuring out more about the atomic structure first was a guy named J.J. Thomson. Okay, Joseph John Thomson was an English scientist, and he was actually working with a thing called a Crookes tube or a cathode ray tube. Okay, and people knew about atoms, and it was basically accepted that atoms make up all matter, but we didn't know what made up atoms or if anything made up atoms. But J.J. Thomson showed that the atom actually does contain some other particles. So this is the Crookes tube or cathode ray tube that J.J. Thomson used to find the electron. And this little green beam that shoots from one end to the other is called a cathode ray, and people knew about these. But what J.J. Thomson did was he actually kind of showed what's going on. So this tube is just filled with a little bit of air, a little bit of gas atoms. Okay? And he noticed that when you take this beam, you can push it around and deflect it. Okay, and he's deflecting it with another charged plate. And he can see here that it moves away from it, and then if we turn it around and use the other side of it, that instead of being deflected away, it's pulled towards it. And Thomson realized that this must mean that the beam is charged. So if this beam of light is charged, that charge actually had to come from somewhere. And since the only thing in the tube was a few atoms of gas, a few atoms of air, Thomson realized that the charge must actually be in those atoms themselves. But atoms are neutral, right? There is no charge in the air when you walk through it. Atoms are neutral. So these charged particles must be contained within smaller things in the atom. So these charges are actually part of the atom, and the atom can be broken down. Now we call these particles electrons today. Thomson called them corpuscles, but electron was the agreed upon term. Okay, and so Thomson's model looked a little bit different than Dalton's. Remember, Dalton said that we only had one thing, and it was a solid sphere, so we weren't going to be able to break that down anymore. But Thomson's experiment just showed that we can't just consider a solid sphere anymore, because we have to consider particles inside that sphere. So what we get is the Plum Pudding model of the atom, and you'll notice we still kind of have this sphere around the outside, but we also have these little dots in it. Okay. Now, the electrons, these are what these little dots are representing. They are negative charge, so every electron is negative. They all have negative charges on them. But the atom must remain neutral, so the rest of this that makes up the rest of the atom is positive. Okay. This is called the Plum Pudding model after plum pudding, where the electrons are plums and the rest of the pudding is the positive part of the atom. I like to think about it as the chocolate chip cookie model because I've never had plum pudding in my life. Right? The cookie is the positive part of the atom and the chocolate chips are the negative parts of the atom. But this is Thomson's model of the atom, and you'll notice it is a little bit different than Dalton's model because it's no longer the smallest part. Okay, atoms are no longer the smallest pieces. Now we have electrons inside the atom. Okay? And so this was Thomson's model, and this was actually developed right around the early 1900s. Okay? And Dalton's model lasted for 100 or so years, but Thomson's model is only going to make it about 6 or 7 before we realize, oh, something else has got to be going on because we have more things that this model can't explain. The reason Thomson's model did not last very long was because of this guy. His name is Ernest Rutherford, and he was a scientist from New Zealand. In fact, he actually worked with Thomson to discover the electron in the late 1800s. 1897 was when they announced it. Okay? But then he continued to do some more work, and he discovered in 1911, so about 14 or so years after they discovered the electron, Rutherford discovered that the positive charge and most of the atom's mass is concentrated in the center, or what we call the nucleus of the atom. Now remember, Thomson in his model, well, let's go all the way back to Dalton. Okay, Dalton's model said we have these tiny solid blocks, that's it, there's nothing in them. Then Dalton said, or Thomson, so Dalton, okay, Thomson said, well, that's not entirely going to cut it because we know there has to be charged particles within this atom. So we're still going to have this tiny block, but now we're also going to put some electrons in it and we have these charged particles. Well, Rutherford said, actually, this one's not quite right either. So what Rutherford did was he did what's called the gold foil experiment. It's another very famous experiment in science. Okay, and he shot alpha particles, and alpha particles are actually just tiny little positively charged particles. They're radioactive decay. They're emitted by radioactive elements. And he shot these at gold foil. Okay. Now gold is very, very malleable. You can bend it and shape it into a very thin foil. So we've got just a few atoms thick, and he took these tiny little alpha particles and he shot them at gold. And he expected that these particles would be small enough and have enough energy that they would just basically find their way through this foil, this tiny thin sheet of foil, and they would hit this film on the other side. So they would get deflected a little bit, but they would move right through the foil. But when he actually went to do the experiment, he saw something a little bit different. So we have a radioactive source up in the top left, and it's going to start emitting alpha particles at this gold foil. And you can see a lot of them are hitting straight across, which is what Rutherford expected. But if you look up in the top side of it, you're going to see that occasionally an alpha particle bounces back away from the gold foil. And Rutherford didn't expect this at all. He thought these alpha particles should just shoot right through that gold foil. There's not a lot of mass there. There's not a lot to stop these alpha particles. Okay? So why is it that we keep getting these things that are bouncing back? Well, this is what his hypothesis was. He said, well, what if there's something that's tiny and dense in the middle of the atom that actually has most of the mass, and so when an alpha particle hits it, it bounces back. The majority of the time it can go through because the majority of the time it's in open space. After seeing that these alpha particles sometimes would bounce back, a lot of times they went through, but occasionally they bounced back, he was able to conclude that there must be something in the center of the atom that is stopping those alpha particles from going through and is massive enough to actually bounce them back the other direction. Okay? So he came up with the nuclear model, which is close to the model that we use today. He said the majority of the mass and all of the positive charge is located in the dense center of the atom. Okay? So he actually hasn't changed the shape of the atom. It's still a solid, or well, it's not solid anymore. It's still a tiny little block, but now he says most of everything is right here in the middle. And there's a few electrons on the outside. This most of everything, this is most of the mass, this is most of the charge, this is most of the atom is right there in the middle. Okay, and that center is called the nucleus. Now, the electrons are actually out here. Okay? And electrons are tiny, minuscule little things. They don't have very much mass at all. They have negative charge. They're floating around the outside. Okay? So this is a better cartoon, and basically the atom is still neutral, but now instead of tiny solid blocks, we have mostly empty space. The electrons are zipping around the outside, filling up this space, and then the nucleus is in the middle, but the majority of the atom is actually empty space. And this is actually really, really close to the atomic model that we use today.